We're going to try and wrap up 9.3 and 9.4. This is the last time we meet before the final, but I'll talk about all the details in terms of like when the final is and times and all that. We had started talking about polar equations last time, and we're going to continue that. One thing, I did post the solutions to the last questions in 8.7. I don't know if you remember, I told you that I hadn't done a couple of them. Well, I did those yesterday and I posted them online. Today after class, I'm going to go down to my office and I'm going to do all the homework problems from chapter 9, 9.1, 2, 3, and 4. So I know some of you said that you would want to be there. If maybe you're welcome to join. Yeah, just keep your mouth shut. Yeah, don't talk to me. I'm just kidding. Yeah, just shut up. Okay, so let's take a look at this equation, r equals 2 cosine theta. We had looked at two examples before this. The examples that we looked at were almost like constant functions. All right? If our radius is fixed at 3, it would just draw a circle with radius 3. So we can almost look at that as like a constant function. Like our traditional functions, that's like y equals 3 is a horizontal line. And then when we have theta equals pi over 4, that's like x equals 2. That's like a vertical line back in the Cartesian. But here in polar, it's going to draw the diagonal because it's all the points where your angle is fixed at pi over 4. So we talked about that last time. Here, we're transitioning to the first kind of useful function. And that's where r is truly a function of theta. All right, so r is 2 cosine theta. The graph of it's there in your packet, but I want us to actually figure out where that graph comes from. So what I'm going to do is make a good old t-table. I'm going to put theta here, and I'm going to put r here. And I'm going to do it that way because r depends on theta, right? Yep. So let's just plug in some values for theta. So let's start with 0. If theta is 0, then I'm going to get what? 2, right? So here, I'm going to start graphing this over here. Here's what this means. And remember I showed you what polar graph paper looked like last time? Yes. I'm not going to draw polar graph paper, but I made this little thing here today. So this is going to be my direction arrow. This is going to give me my arrow of which way I'm pointing, okay? So right now, theta is 0 means I need to be pointing out the x-axis. And then I need to walk out 2 units. And so I walk out, let's say 1, 2, right there, and I place a dot. Okay, that's my first point. And now I move to the next theta. So let's pick something we know. Let's go with pi over 6. And that's going to be 2 cosine of pi over 6, which is 2 times root 3 over 2, which is just root 3. And root 3 is about, I don't know, smaller than 2, bigger than 1 point something. You can get your calculator out if you want. You can tell me exactly while I'm going to draw some common angles here. That's 45. That's 30. What is it? 1.73. So imagine if I were to take a circle, right, of radius 2. Let me try and do this. If I were to take a circle of radius 2, it would be something like this, right? So when I go out, thank you. So when I go out and I aim pi over 6, that's 30 degrees, I'm going to walk out 1.7 something. So not quite 2, I'm going to be somewhere in here, right? And so I don't need that. That was just a reference so I knew how far to go out. And then I keep going, right? So let's do pi over 4. I'll pick up the pace here in a second. 2 cosine pi over 4. Cosine pi over 4 is root 2 over 2. This can turn out to be root 2, which is about 1.414. So that is going to be point pi over 4, which is 45 degrees. Walk out 1.4, so something like that. You get the idea? Yeah. Okay. So I start drawing this thing. Now things are going to start to get a little interesting when we get to like, let's see, pi over 2. Because 2 cosine of pi over 2 is going to be 0, right? because cosine of pi over 2 is 0. So that means I want to aim, right? I want to aim pi over 2, which is straight up, and I want to walk out how far? Nowhere. So just stay at the origin. So what's happened is if I were to have connected all these together with a curve, I would get, looks like a top half of a circle here, doesn't it? Yes. Okay, now here's where things get really kind of interesting. Let's continue our angle. So we've done a couple angles between 0 and pi over 2. Let's go to like maybe 3 pi over 4. Okay? So if we aim at 3 pi over 4, 3 pi over 4, then we're going to get 2 cosine of 3 pi over 4. Cosine of 3 pi over 4 is what? Negative root 2 over 2, right? And so you get, negative root 2. You're getting a negative radius. So what that means is we're going to go and point 3 pi over 4, so we're going to point this way, but we're going to walk out negative. We're actually going to walk backwards. And we're going to go backwards root 2 over 2. Just root 2. And that would put us, somewhere down here. Oh, no, it's about right there. Okay? Yeah, and if I were to continue to do this, if I were to put more points in here, every time my angle is in the second quadrant, right? Every time my angle would be in the second quadrant, can you tell me about the radius? What would it be? Negative. It would be negative, right? Because in the second quadrant, cosine's negative. Yeah? Yeah. So every time I'm here, I should be in this quadrant. And it turns out, let's go to pi. Let's actually try and get out of the second quadrant. If we went all the way to pi, where would we be? So 2 cosine of pi. Cosine of pi is negative 1. So this would be negative 2. So as I'm pointed out pi, I walk backwards 2 and I'm back here. See that? So what I've done is I've drawn an entire circle, right? But it's been kind of shifted over. You'll see that? So this is a circle with radius 1. Yes? But it's shifted. And I drew the whole thing in what interval? What was my 0 to pi? From 0 to pi, I drew the entire circle. It's kind of interesting, right? Just out of curiosity, what would the Cartesian equation of that circle be?
X squared plus y squared is equal to...
So x squared plus y squared equals r squared is the general equation of a circle centered at the origin.
This has just been translated into...
Yeah, hold on. I'm going to do one thing. This is the more general equation for circles, right? This is if you're centered at HK. Where's our center? 1, 0, right? So this is actually x minus 1 squared plus y minus 0 squared, so y squared equals, what's the radius here? 1. Do y'all agree with that? Yep. Now the reason I'm showing this to you is because there should be a way to go from Cartesian to polar. Like if somebody gave you this circle, could you convert it to polar? So let me show you how that's done. I know in Cal 3 we do this. So let me show you how I convert that to polar. Everyone understand that's the Cartesian equation of that circle? Okay, so what I'm going to do is I'm going to just expand out this side. This is x squared minus 2x plus 1 plus y squared equals 1. Do you agree with that? And then cancel out your 1's. Subtract 1 from both sides. So you get x squared minus 2x plus y squared equals 0, right? Now, what was the standard conversion to go from Cartesian to polar? Y equals? You'll need to remember what these were. They'll sound like you're on the right track. Cartesian to polar. What was x and what was y? R cosine theta, r sine theta, right? Isn't that the equation for x and y? So go to this equation here and replace x with r cosine theta and replace y with r sine theta. And let's see what we get. So let me take this over here. I get r squared cosine squared theta minus 2r cosine theta equals, or plus, sorry, r squared sine squared theta equals 0. Y'all still with me? Yeah. That's x squared minus 2x plus y squared equals 0. Now, you recognize that those, if I factor an r squared out of just those two, I get cosine squared plus sine squared, which would be 1. Yeah? Okay, so if I factor out, I'm going to get r squared minus 2r cosine theta equals 0. Did I do too much, or is that all right? Is that all right or no?
Yeah, you're good.
Sure? Okay. And now let's try and solve this for r. Because remember, for polar, you want r to be a function of theta, right? So let's solve it for r. If I factor an r out, I get r minus 2 cosine theta equals 0, right? And now you have factored the left side, it's equal to 0, set each factor equal to 0, right? So if I set the first factor equal to 0, I get r equals 0. And then the second factor, r equals 2 cosine theta, right? Understand? Yep. Now, r equals 0. If I were to ask you, forget this right here. If I just said, hey, this is a polar equation, graph it, what would you graph? A dot at the origin. That's all it would be, right? It's just a dot at the origin. Okay, is the dot at the origin on this graph? Yeah. Yes, okay. Now, how about this one? If I ask you to graph that, well, we just did that, right?
The other dot.
So this draws the rest of the circle. So this is kind of overkill. You actually don't need that piece, but the two together do draw that circle. That's kind of cool, right? That you can convert from Cartesian over to polar.
That's math.
Okay. So I'm going to bring up the graph of this one, even though it's right there in front of you, because there's some stuff I can do on this animation that's going to be kind of important. What I've done here is I have used a green line to represent that little arrow that I had here instead. So just keep track that keep in mind that the green line is showing the direction that you're pointing. All right. So when I point out to pi over 6, I went out 1.73. And then as I move around, I'm going to have a problem when I get to pi over 2, but it's only because my algorithm can't handle a division by 0. So it's going to freak out here. And then that's 0. Oh, there it goes. And then once I get past it, what you can't really see here is I'm pointed in this direction. And I'm going backwards because my radius is negative. And then I move myself around. Okay, understand? All right, let's look at another one. The cardioid. Cardioid is named after the shape you get. It's similar to a heart. So call it the cardioid. But let's take a moment to see if we can graph it. I'm just again going to do a quick table. And you know what? This is as good a time as any to realize that your calculators can graph these. So remember last time I was showing you how to go into parametric mode? Yes. Okay, there's also a polar mode. So if you'd like, you can take your calculator out and you can...
Yes, there is. You
can switch your mode over to polar and then go to your graphing utility again. And all it's going to say is R1, R2, R3. And so you can have multiple polar graphs here. Now, I don't recall, yeah, my calculator wants me to use theta as my variable. And I don't even know where my theta key is.
You can usually just put your X. It'll automatically do it.
Whoa. Okay, let me do it. Hold on. I haven't done a polar graph in a long time. No, it doesn't do X on mine.
Do you have an 89?
I have an 89.
It's right up here. It's your same pi button.
Oh yeah, there it is. Okay. Yeah, so I have to use theta. Some calculators have a key that says like x comma t comma theta, and it will automatically plug in that variable. So just try to plug in 2 cosine theta, or t or whatever it is on yours, and graph it and see if it graphs that circle or not for you.
It does.
And then go to your window, and it should say something like theta minimum 0, theta max. I think the default is 6.28, which is 2 pi. 2 pi, right? So what I want you to do, if you're looking in your window, is change that theta max to just pi. Is it still going to draw the circle?
It should.
It should, right? Because we did the whole thing. Try and graph again.
No, it cuts off the.
Mine
No?
doesn't even graph.
No, it should.
Mine cuts it off after I changed it to pi. It drew it when it was.
Mine does like
Yours isn't drawing that right. Hold on.
That's what I'm saying when I changed it to pi.
zoom in.
Oh, I'm sorry. We're drawing. Sorry, you're doing this. I was doing the one before this. I apologize.
Oh, okay.
My fault. There was confusion. Y'all want to do this one? My fault. I thought we were still doing 2 cosine theta. Okay. Y'all want to do this one? Never mind.
Sure, why not?
Never mind.
I thought we were.
Let's stick with this one. Change it back. Change your window back to 0 to 2 pi. And then you should have the whole graph.
It cut off the interesting.
Oh, there we go.
Yeah. Okay, that's just some, FYI, your calculator can do this. That's kind of cool, right?
Mine spit out the numbers. Mine doesn't spit out the graph. Mine's freaking out.
Yours didn't? Are you in radian mode?
Whenever I switched it,
You sure?
I just
No.
Go into radian mode.
Oh, that's right, because I
Yeah, these things are real picky.
Yes, it worked.
It works if you're in radian mode. My advice to you, if you're moving on and doing more math, is to always leave your calculator in radian mode.
Well, I was
Okay.
in physics, so I had to have it in
Well-
physics.
Yeah, I'm saying math class. I'm saying if you're going to go on and do more math. Okay, I need to move on here. So let's just verify that we get this. Let's plug in some values of theta and see what we get for r. If we plug in 0, we get 1. If we plug in pi over, let's say, 4, okay. Pi over 4, we get 1 plus root 2 over 2. If we plug in pi over 2, we get 2, and so on and so forth. So if we actually now go and use that little arrow and start drawing our points, we are going to get some negatives. Are we? Are we ever going to get negatives?
What sign? So
Yes.
Yeah.
Will you ever get a negative radius?
No, because it's not going to be.
You will never get a negative radius.
It will never exceed that.
That's right, because you will get a negative here at some point, right?
Yeah.
Once you get where? Once your theta gets past pi, right? You're going to start getting negative values for sine. But the biggest they'll ever be is -1, right? So you'll never overcome that. So when we graph this, our radius should always be positive, right? You agree? So that's the graph of this, all right? Now it is a heart if you flip it over, I guess.
or a butt.
It's kind of a weird, yeah, it's a butt. They call it a buttocks, a cardioid or a buttocks. All right, this next one is interesting. I'm not going to do the table on this. Okay, I'm not going to do a table for this one. It's r equals cosine of k theta. And let's just look as our first example, r equals cosine of 2 theta. So I believe I already have that set right there. Yeah, that's cosine 2 theta. So without making the table, when I plug in 0 for theta, I'm out here at 1. Can y'all see this? Do I need to make this bigger? Or are y'all all right? Bigger? When I'm at 0, right, for my angle, it looks like I'm at 1. Yeah? Okay. The thing you really have to pay attention to with these polar equations is more the restriction on your theta, like what it takes to draw this. So let's try and keep track of what it takes to actually draw this thing. When I start, okay, pi over 12, I'm going to go up and start drawing that first, like, petal. They call this a rose, a 4-leaf rose. This, I'm starting to draw the first petal. I started here, and I'm starting to trace out this top piece, right? And then I keep moving. Let's see, and I get to pi over 4 is where I'm at the origin. So I've done this much, right? Now, your instinct may be that now what I'm going to do is come and draw this next petal, but that's not at all what's going to happen. Now what's going to happen is I'm going to start drawing the bottom petal, okay? I'm going to get division by 0 there. That's just my computer having a problem with the way I'm telling it to graph. So don't worry, you're not getting division by 0 when you plug in theta. So now what I've done is I've started here at 0 and I've drawn like this and come like this. Now the reason this is important is because we're going to be talking about arc length in a little while, and we're going to need to know when to start and stop, and we're also going to be doing areas, and so you need to know when the region you're talking about starts and stops. So right now, as it is, this curve has not enclosed a region, has it? No. If I keep going, though, it will, at that point, have enclosed a region. So later on, meaning very soon, I'm going to want to know the area of that region. So what will your restriction on your theta be? So where are we right now? We're at 3 pi over 4, right? That's where we are now. But we don't need this part, okay? So you have to remember when did that take place. So you have to back it up, and it was at pi over 4, right? So when we do our integration in a little while, we're going to be going from pi over 4 to 3 pi over 4, okay? So it gets a little tricky because you're drawing, like if you didn't have the computer to aid you here in this, you'd really have to pay attention to the way you do it with your table.
If the question was, what is the length of the arc length for this one, would you have 2 of them right now? Would you have where you start and then all the way down to -1, or x is 0, y is -1, there's one arc length and then a second one on the upside?
Well, it just depends on what you're being asked. If you want the arc length of the whole thing, then you have to figure out what your total theta is. If you ask for arc length right now, from 0 to 3 pi over 4, it would just give you the length of this black part that I've drawn. That's it. It won't give you anything else.
That's cool.
Yeah. Okay, so let's see. We get over here. Now let's see when we get, what happens when we get to pi? So at pi, now we're here, right? Let me keep going here. Where's 2 pi?
All the way over
Back here. So it looks like I drew the whole thing from 0 to 2 pi.
So if we wanted to know the area of all that, we just integrate from 0 to 2 pi.
If we want to know the area of the whole thing, it'd be probably best just find the area of 1 and multiply by 4.
Now, is that,
Yeah, let me get to that.
Okay.
Yeah, I'm not there yet. What I'm trying to get you to pay attention to right now is that as you run through your values of theta, you have to be very careful and pay attention to where you are on the curve. You cannot just assume that, a lot of people would assume that if I want to draw this piece up here, that my theta needs to be between pi over 4 and 3 pi over 4. But that's not what's actually happening. Between pi over 4 and 3 pi over 4, you're actually drawing this piece here. So it's a little bit tricky. Make sense?
So is it like when you're in the first and second quadrant, you're actually drawing?
I'm actually drawing down here in the third and fourth. But it's just because of this function. Okay? It's just this specific function. It's not like that all the time. So let's see what happens if I change this. Right now I did cosine of 2 theta, right? Let's see what happens when I change it to cosine of 3 theta. So there's my picture. All right. So let's start going through this. I start out at 0, right? Oh, I did the wrong one. Sorry, I start out at 0, and I'm right here at 1, okay? And then as I move through, goes up, it's going to go back the other side, just like the other one did, go down, come back up, back around, and we drew the whole thing in from 0 to pi, right? So if I went 0 to 2 pi, I would draw 2 of these right on top of each other.
That actually makes sense though, because when you increase the number of data, it increases the...
That's right, because when you're looking at a trig function and you change the number in front, that changes your period, doesn't it? The bigger that number gets, the shorter your period gets. So it should take less time to draw to go all the way around. Okay, let's increase it. Let's go to 4. Whoa.
Wow, there goes your point.
So I guess I was lying.
What? How? No, you're right. Look, when it was 3, we drew more petals. Even though it was 3 petals, if we would have gone from 0 to 2 pi, we would have drawn 6 petals,
okay.
right?
Ooh, you said right on top of each other.
On top of each other. But we would have gone through 6 actual petals.
Okay.
Right? When k was 2, how many petals did we draw? 4. When k was 3, we drew, between 0 and 2 pi, we drew 6, right? On top of each other. Here, we draw 8. And let's try and follow the path of this one. I'm just going to play it and see what happens. That's a little too fast.
So does that mean that when we go to 5, they're going to be
10? Yeah, 10, but they will be on top of each other. So this one, what's happening here, when I draw this, here's what's happening. If I were drawing this, this is going like this. Whoa.
So all the odds get stacked and all the evens
Get drawn out.
Yeah. Yep.
Why is that?
See what I'm doing here?
Looks like the Jimmy Neutron symbol.
And so on and so forth. So here's the 5, right? But I would draw actually twice. If I went from 0 to 2 pi, I would draw right on top of it.
Why the discrepancy for the even odds? Is it just how the numbers fall, that the odds you stack it up and just have a thicker line and trace your own work twice, and the evens you don't?
Yeah, it's just kind of the way it is. Yeah, it's just the way it is. I mean, we can get into it. I mean, you're trying to divide up by an odd number, trying to get an even number of petals into an odd, so there are things we could, but it's not worth our time. Okay, dy dx. So first question, what's the slope of the tangent line? Second question, what's the area of a polar curve? Third question, what's the arc length? So it's the same 3 questions that we asked for parametric, but we're going to do it for polar. So I'm not going to derive the formula for this. It's not that hard to derive, and the book actually derives it, but it's a much more complicated formula than what we have in the other parametric. If you remember the parametric, the formula for the slope of tangent line, do you remember it? No? Okay. It was... That's right. So it was dy dt over dx dt. That was your slope of tangent line for parametric. Here it's dr d theta times sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. That's not very natural, right? All right, so let's do this example. Given the equation r equals 1 plus sine theta, find the slope of the tangent line when theta is pi over 3. So let's first find dy dx. All right, we're going to need some derivatives in here. So let's get that top left corner, dr d theta. What is the derivative of the radius function with respect to theta? So what's the derivative of this? 0 plus cosine theta. So just cosine theta? Cosine theta times what? Sine theta plus r cosine theta over dr d theta, which was cosine theta, times cosine theta would be cosine squared, and then minus r, and then sine theta. Right?
So can you like factor out a cosine on top and bottom and then cancel it out?
We can factor cosine, but we don't have one to cancel because we don't have a cosine over here. Right?
It's not all, okay.
Yeah? Okay, this all right? Now, we can do a little bit more. Do we know what r is? What's r? 1 plus sine theta, isn't it? So this is actually cosine theta, sine theta, plus r, which is 1 plus sine theta, times cosine theta, over cosine squared theta, minus r, which is 1 plus sine theta, times sine theta. And we could go through the process right now of cleaning this up, right? Trying to, at least. Now, if all I was being asked was part A, if that's all I was being asked, I would just plug pi over 3 in for everything here and I'd get my answer. But the problem is part B and C want to know when this tangent line is horizontal and vertical, which means I have to set this equal to 0, right? So I'm going to need to do a little more work at some point. But let's start with part A, all right? Let's start with part A. Part A, at pi over 3, dy dx is equal to, so we have to plug things in here. This isn't going to be fun, but pi over 3. Pardon?
Where it says 1 plus sine theta cosine theta.
Right here?
Yeah, is that squared?
What squared?
The cosine?
No.
No.
Mm-mm.
Oh.
Why would it be squared?
I just cosine times cosine.
I thought you were multiplying by the cosine of theta and then distributing it. But
He means
This r is 1 plus sine theta,
I think he means the denominator where you have cosine times cosine.
cosine squared.
Well, never mind.
no, where you said cosine theta times sine theta plus r cosine theta.
Yes?
They're distribute.
That comes from up there.
What does what distribute? I don't.
The cosine doesn't distribute, does it? It's just
Oh,
multiplying
he's
cosine.
asking if you can multiply cosine theta into there, so cosine theta times 1, cosine theta times sine theta, then add cosine theta. sine
Okay,
theta plus
let's
cosine.
plug in pi over 3. Look, we can do a lot of things here. Y'all are. Okay, let's plug in pi over 3 into this. Cosine of pi over 3 is what? Root 3 over 2. Times 1/2 plus 1 plus 1/2 root 3 over 2 over root, so 3/4 minus 1 plus 1/2 and then 1/2. And that's just a number, right? So we could get that answer. I don't want to do the math. You get the idea. That's how you apply the formula. Now, let's get to part B, because part B is more interesting. And I'm going to scroll this thing up to give myself some room. Okay, so when it's saying for part B, find where the tangent line is horizontal, we want to know when dy dx is 0, right? Here's dy dx. If I want to know when that's 0, since it's a fraction, I only have to look at the top. I have to set the numerator of that equal to 0. So I need to set cosine theta, sine theta, plus 1 plus sine theta, cosine theta, equal to 0. And that's a trigonometric equation, and I need to solve it. So yes, I will have to do some distribution here. Cosine theta, sine theta, plus cosine theta, plus cosine theta, sine theta again, equals 0.
We can factor some stuff out.
Yep. You can factor cosine out. If you factor cosine out, you get sine theta. How many sine thetas will I have? I have sine theta here, I have a sine theta there also, right? So I'll actually have 2 sine thetas plus 1 equals 0. And since it's factors, set them each equal to 0. So cosine theta equals 0. And 2 sine theta plus 1 equals 0. All right, where is cosine 0? Pi over 2 and 3 pi over 2, right? I agree, but we are not restricted on any interval here. We need a general solution this time. So the way I like to do my general solutions is I go and I look at a unit circle. I say at what angles are cosine 0, and that's here and here, right? And since they're directly across from one another, what I can do is start with almost like a reference angle, pi over 2. And then from that, I just need to add multiples of pi to spin around to get all these solutions. You can just say n pi, pi over 2, yeah. N times pi over 2. Now you could also use a k. Sometimes we use k, depends on your pre-calc class. But here it's understood that n is an integer.
But like, should we add like a 1 or a minus 1 though? Because like if you plug in 2 for n, then it will be pi, and pi is...
Yeah, this right here would give us the rotation, right?
Oh.
Like this. This will make you jump by pi over 2, right? What we don't have is where do you start. So what you have to do is add to this where are you actually going to start from. Pi over 2. I'll write it like this. I kind of ran out of room. I'm going to write it the other way. Pi over 2 plus n times pi over 2. See if this makes sense. So it says your angle, you need to start at pi over 2, right? And then from that, add multiples of pi over 2. So either add nothing, which means you just stay there, or add 1 pi over 2, which would put you down here, or add 2 pi over 2, so here and then back up, or 3, or negative. Huh?
Would it be pi to get that 180?
No.
No, yeah, hold on. No. That's right. It would be pi.
Okay.
Yes, it would be pi. I don't know why. No, I know why.
I don't know, because you checked out.
Yeah, I checked out. Yeah. That's
That's the sign.
the sign that we're done? That is the sign. That is the sign. Look, I was saying pi over 2 went from here to here.
Okay, so now we start at pi over 2.
Start at pi over 2,
We
add multiples of pi, 180. Yes. 180, 180, 180, 180.
Nice catch.
Yeah, thanks for being awake still.
We were all.
I know Nathan wasn't going to catch that.
Fuck no.
You said you checked out, so.
He's sitting there doing this,
So-
tapping out.
I'm hitting the brake right
So would the
now.
vertical be in pi since you're traveling from one vertical to the other?
Would the vertical be what?
He's backing out.
What
So you're going from 0 to pi, then pi to 0.
would what vertical be? Are you talking about part C?
Yeah.
Oh, I'm not done with B yet.
Oh, okay.
This is some of the solutions, not all of them. I still have to solve this equation. Let me get this first, and let me pay attention. Okay, so sine of theta is -1/2, right? So where on the unit circle is sine -1/2? Well, sine is your y-coordinate. That's going to happen here
And then on the other side.
and here.
4 pi over 3.
So 4 pi over,
Wait, isn't that pi over, it's 7 pi over 6 and 11 pi over 12 or whatever?
Yes, isn't it?
you said 4 pi over 3, right?
It's 5 pi over 3. I don't know.
Yeah, okay. So what's
Better. I was like,
what's this angle right here?
That's
a good
To
question.
me, that looks like 7 pi over 6.
7 pi over 6. 7 pi over 6. Okay? And you cannot add pi to jump to this one, or pi over 2. These are not directly across from each other. So we're going to have one set of general solutions. It's going to be first where we start, 7 pi over 6. Plus we got to get all the way back to it, 2 pi n or n times 2 pi. Doesn't matter where you put that in. Okay? That's one set that gives me these. Now to get these, what's the angle?
11 pi.
11 pi over 6. and then plus again to get back to it 2 pi n. So now I could start actually plugging in values of n for each of these sets and start creating a list of solutions. That's the way it's done. Okay? That's where we have flat tangent lines. Let's just check one. Let's just check 7 pi over 6. Let me go to the graph. Right, if I let n be 0 here, at 7 pi over 6, I should have oops. No, that's not it. There it is. 7 pi. Whoa. What happened?
We don't even know.
No, you're right. Look at the red dot.
Oh, the red dot. Yeah. Okay, there it is. I didn't see the red dot. Slope of the tangent line. Remember, the green is only my angle, right? Like which way I'm pointing. So slope of tangent line there is 0. Got it? Okay, now let's do part C.
Now we have to find.
Where's the tangent line vertical? So we need the denominator. What was the denominator? Because I've erased it.
Squared theta minus sine squared theta minus sine theta.
Minus sine squared theta. What? No.
Minus sine.
Oh, right. So it is cosine squared minus 1 plus sine theta.
Sine theta. Okay. Equals, and we want to know when that's 0 because that will give us division by 0, right? Mark, I think you had already multiplied it through, right?
Yeah.
Okay, so cosine squared theta minus sine squared theta,
I do apologize.
and then minus sine theta equals 0. Ooh, can't factor.
There's an identity there.
There's some identities here. How about we do this? Because we've got sines here, we don't have sines here. Let's just use the Pythagorean identity to rewrite cosine squared. Cosine squared is 1 minus sine squared. This, if you remember pre-cal, which I know was a long time ago, this is the way we solve trig equations. I mean, there was different methods, but this is the way we did it. So now we're going to have a quadratic in sine, aren't we? I have 1 minus 2 sine squared theta minus sine theta equals 0. And I'm going to convert that into 2 sine squared theta plus sine theta minus 1 equals 0. And what I've done there is just multiply both sides by -1 so I could get a positive coefficient, leading coefficient here. And that is a quadratic type, isn't it? It looks quadratic.
Yeah, substitution.
So, yeah, I can do a sub, or I can just go right. I'm going to go right to it. Like this is just 2 sine theta, and then I'm hoping this is going to work out. Is it going to work out? Plus 1 minus 1. So does this work? 2 sine squared
Yeah.
plus 2 sine theta minus sine theta
Yeah, and then
minus 1. And now set each of those equal to 0. 2 sine theta minus 1 equals 0, and then the other one, sine theta plus 1 equals 0. This is sine theta equals -1. This is sine theta is a half, right? So we got another set of general solutions, 2 sets of general solutions. So where is sine a half? Go to your unit circle. That happens here and here, right? It's kind of the opposite. So we have pi over 4, pi over 6. That pi over 3 is up here. Pi over 6 is here. So pi over 6 plus a full rotation here, 5 pi over 6 plus a full rotation. Sine is -1. That's just here. It's the only place it's -1. So 3 pi over 2 plus 2 pi n. I hope that this whole thing kind of rings a bell. I know it's been a while since you've done solving trigonometric equations and
Now we know
getting
why.
general solutions.
Now we know why we do this.
Yeah. All right, moving right along. 9-4. All right, here we go. Let me know what school. I want to make sure I keep my kids away.
Don't worry, I'm not gonna go past third grade.
Yeah, that's even scarier.
They're gonna stick to like x minus 2 equals 0.
They don't even do algebra.
You're
gonna be sticking to 2 times 2 equals 4, 3 times 3 equals 9.
Okay, polar curve. So
like next term, I'm okay with it.
you're asking about the, how we do areas, right? So look, I'm going to do just a real general concept of this. I'm not going to get into it in too much detail. First of all, we all have to agree with this. If somebody gives you an arc, okay, an arc like this, and you have an angle here, theta, and you have a radius, that the area of this is 1/2 r squared theta. We have to believe that this is true. Right? So that is a formula. That is a formula. Right? And what's cool about this formula is that if you try and find the area of an entire circle, okay, then what's the radius? R, let's say. What's the angle that you sweep through to create the whole circle? 2 pi. So if I replace this with 2 pi, what does this become?
Pi r squared.
Pi r squared, right? So this is like a more general formula for the area of a circle. But we have to believe this is true before I can convince you as to why the area formula for polar curves is that. So here's how we do it.
That makes sense actually, because that's an infinite, because d theta is just the infinitesimal slice.
Yeah, so imagine you have a polar curve, right? And let's say this polar curve does something crazy and it's drawing it, and then let's say we just stop right there. All right, so we have some angles, right, that we're going to sweep through. And imagine that if I stop here and I start over here, I want the area of this in here, right? I want that area, but I'm using polar coordinates. So what I do is I take an infinitesimal slice, and we used vertical and horizontal rectangles in the past. Not this time. What we're going to do is we're going to take infinitesimal little sectors. No, they're going to have a little arc on the end of them, like that, which is what I just showed you we needed the formula for.
And it's all
Right?
right if it's
What?
over the...
It's okay if it comes over, because remember what we're going to do is take a limit and let the number of these go to infinity. And so they're going to get smaller, and the error here is going to go to 0. Just like our rectangles, when we did areas, we had rectangles. We approximated, and we had all that error in there. But it was okay because we let it go to infinity. So same idea? Okay? So I need a formula for that area. What's the formula for the area of that little piece? 1/2. What's the radius? What's the radius? It's r. It's actually the function of theta, isn't it? Because that radius changes. As I move my angle, that radius changes. So this is actually, the distance from here to here is f of theta. So f of theta times the angle itself, right? The angle in here. That angle is not theta, it's d theta. It's my little infinitesimal change in theta, right? I'm letting that little arc, that little sliver is just a little change in theta in there. So this in here is d theta. So if that's my angle, it goes here. Understand? So that's the area of one slice. If I want them all, right, I'm going to do an integral, right?
Theta is the square.
I forgot to square it. Yeah. Okay, so squared. I put squared on the other formula, right, when I put it up there?
Yes.
Okay. All right. So this is it right here. And then A and B are the restrictions on theta. Okay, so if you start out at 0, and let's say you stop at pi over 3, then it'll go from 0 to pi over 3. So let's do our first example. Find the area of a circle radius r. This is the third time I'm going to have proved this formula to you. We did it in Cartesian. It was quite a bit of work. We did it in parametric. It was really pretty clean. And in polar, it's almost a joke. All right? So what is the area? Well, how do we draw a circle? Tell me, what is the equation of a circle of radius capital R in polar coordinates? What's the equation? R equals, now R equals 1 would draw me the unit circle. R equals 2 would draw me a circle with radius 2. R equals capital R, right? That is the equation, right, of a circle in polar coordinates. Do you all agree with that? Yeah. Okay. So this is my f of theta, isn't it? Yeah. So according to the formula for polar coordinates, the area will be the area of this circle. Going back to the formula right there, 1/2 r squared theta, right? So the area will be integral a to b.
So 0 to 2 pi.
Yeah, so when we draw this, we want to just draw it one time, right? So 0 to 2 pi, 1/2 capital R squared d theta. And 1/2 capital R squared is all a constant, isn't it?
Yeah, we pull it out.
You can pull that out. So 1/2 capital R squared integral 0 to 2 pi of 1 d theta. Antiderivative of 1 with respect to theta is theta. So this is 1/2 capital R squared theta, 0 to 2 pi. 0 doesn't matter. Plug in 2 pi, you get pi capital R squared. The 1/2 and the 2 cancel out. But we did it with parametric. And what happened was when we did it with parametric, we still had to do a little bit of work. There's still a little bit because we had some sines and cosines in there. Here, it's just immediate. Okay? All right, so that one was too easy. Let's move on to one a little harder.
You're gonna put that on, right?
Yeah, yeah.
I think that's a good idea.
Find the area enclosed by one loop of the 4 petal rows, 3 cosine theta, so 3 cosine 2 theta. So I have up here the graph of this. Now this, what you're seeing up here, this little interactive thing right here, this is not mine. I don't want to take credit for it. This is not mine. But it's really cool because watch what you can do. I found it online. Wolfram has a place where you can go where people share stuff, and someone had created it. So here's what they did. They kind of illustrate how it sweeps out the area. So we want the area of 1 petal. So we do not want to start at 0 and go to pi over 4, do we? Well, I mean, I guess we could, right? And then multiply that by 2. We could do that. We could also, so here's one option. We could do integral from 0 to pi over 4, right? And then 1/2. What's the function? 3 cosine 2 theta, but all of that squared d theta. That's one option. And this would give us just that, right? So 2 times that? We could do that. Or we could start at pi over 4 and go to 3 pi over 4, right? So we could just do this exact same thing, going from pi over 4 to 3 pi over 4, and then 1/2 3 cosine 2 theta squared d theta. We just wouldn't have to multiply by 2. Yes?
Is that thing available for us to use? Because that would be great.
If you go to Wolfram Alpha, or not Wolfram Alpha, if you go to Wolfram's, type in Google Wolfram demonstrations. Okay? Wolfram demonstrations. People make different things and put them out there. So I happened to find this one. It was pretty cool. So you can even restrict the lower angle. So you can bring the lower angle in like that. And so that would be from pi over 4 to 3 pi over 4. Make sense? I started to actually code this up and like make my own, and I was like, let me go check to see if there's a demonstration out there. And I'm glad I did, because
This one's actually pretty
this one does more than I would have, that I had time to put together. Okay, we good?
Yeah.
Could you integrate this?
Yeah.
Yeah? Do I need to do it? I don't think I need to do it. You square this, right? Since you're going to have cosine squared, half angle, and then you work through it. Yes? Okay, we're done.
American.
Let's look at the next example.
Hey, that spiral one was kind of cool. That's what I was saying.
Okay, this one, it says find the area inside r equals 3 sine theta and outside r equals 1 plus sine theta.
Okay. So they just want that like Turkish moon?
Yeah, so they want this thing right here. They want this area right there.
So if you rotated at 90 degrees, it would be the moon of the Turkish flag.
Okay.
Area.
No, I don't know. Do they have a certain, is it a cardioid with a,
The area that we're
Like what we
looking
did
for,
with the
just the area.
two functions.
okay.
Yeah.
I lived in Turkey.
All right, what are we going to do?
I think I kind of got the gist of what's going to happen.
What are you going to do?
We're going to find where they're equal to each other for theta to find the bounds.
Okay, good. So we're going to figure out where they hit each other.
And then we're going to find out it's r big minus r little.
Yeah, so we got to figure out which one's the one on the outside, which one's the one on the inside. So which one is the one on the outside?
The red one.
Do you know? Which one is r3 sine theta?
The circle.
The circle?
The red one.
How could you convince me that the circle is this one? Just do a quick test point. How about this? Let me use theta as pi over 2. So if I go theta as pi over 2, if I'm aiming that way, on the red one I should be up at 3, and on the blue one I should be at 0. And you can check it. If you plug in pi over 2 here, you're going to get 3. And if you plug in pi over 2 here, right? Is that right? You get 2. Right? So I said 0. No, I didn't see that point up there, actually. So we're here. You would have to come back around to get the 0. Okay? So this is the outside. This one right here is outside. This one's inside. So what would happen if I found, well, what if I found the area of just this red one? See how this works. These two angles right here, all right? If I found this entire area right here first, that would be the red one, right? The red one between this angle and this angle, that would give me all that area. And then after I'm done with that, I will subtract from it the area right here, which is the same polar integral on that one. Just subtract the two, and that would give you what remains in between them, right? That's the approach. Okay? So we need to figure out where they hit each other. So the question is, intersection. I need to know when 3 sine theta equals 1 plus sine theta. And this is pretty basic here. 2 sine theta. 2 sine theta is 1. And sine theta is a half. And here, I'm not going to get a general solution. I'm just going to get the first 2 solutions I can find. So theta is 1/2. That's sine theta is 1/2. That's going to happen at pi over 6 and 5 pi over 6. That means I'm going to integrate from pi over 6 to 5 pi over 6, right?